Hi.
Hi.
Yeah, so now I'm audible, right?
Yes.
Is my screen visible?
Yes, it's visible now.
Yes, ma'am.
Okay, so previous data has gone because I forced shut down my laptop, but I think it's okay because hardly anything we wrote there, right? So let's start the course then. So since this is all about generating functions, we'll see many uses of the generating functions and the places where it comes handy to handle problems. Okay, so some of the quick things which one can do using the generating functions are that given some sort of a sequence, you can look for an exact solution to it, which means you can find an exact formula. For the terms of your sequence. Okay. Next thing which you can do is that given the sequence, sometimes it is not so easy to see the formula, but in some cases you can try to find a recurrence relation which gives this, or a recurrence formula instead of a exact formula, right? Exact formula means an explicit formula. Like you plug in the value and you have the answer. Recurrence formula is that you will have to keep applying the values one after another to get the answer that you're looking for. And sometimes when neither of these is also possible, you can use generating functions to find asymptotic formulas, which means that in a long run, what really happens to the sequence. Okay. Also, generating functions can be used to prove unimodality. What does unimodality means? It means that some sequence, let's say, initially increases slowly, and then it starts decreasing. So something like this. At a very slow pace, it starts increasing and then it starts decreasing. So such sequences are unimodal. Convexity, you know, the convex function itself. So sequence being convex in this similar manner. And then prove various identities. Okay. For instance, if let's say I have to, I mean, even the things like when you know that first, first k things from 1 to n, everybody knows this is n plus 1 by 2, right? And just like this, let's say if there is some another expression for it in the sense of this sort of a sequence, then you can prove such identities by expanding this, and show that they are actually the same, which would, let's say, be turn out to be this. So things like this, the identities you can prove to be similar in this fashion. So let's start with the baby example for generating functions. First one being the simplest, which I could think of is, let's say an plus 1 is 2an, where n is bigger than equal to 1 and a0 you let's say take 1. So if a0 is 1, a1 is clearly 2, a2 turns out to be 2 into 2. So this is 2 square and so on. It's easy to see that an is nothing but 2 raised to n, right? Isn't it?
Yes, ma'am.
But we are not dealing with the guesswork, although it's very clear here. So we will see how generating functions are used. So the steps of generating functions are that we, as I said on this page, we always try to, express the sequence as this. So by that, what I really mean is that given some sequence an, we are trying to find a function ax, which can be written as an infinite sum whose nth term is an. Okay, so this is n, not really x. Okay, so express the sequence an as a series where the coefficient of x raised to n turns out to be an. This is the main goal, and this is going to remain for the entire course. Okay, so now applying this particular method in the above example, which said that an plus 1 is 2 times an, right? And n was from greater than equal to 1 and a0 was given to be 0. So once this is the goal, you have an's already in this expression. What is missing is x raised to n. So always given the formula for the sequence, multiplied by x raised to n and then sum from 0 to infinity, right? This is how you're going to receive this. So let's start. So you're going to get summation an plus 1 x raised to n and starting from 0 to be equal to 2 times, I can take 2 out, right? an xn n greater than equal to 0. Correct? So this is nothing but the ax itself, 2 times ax. And what is this really? So let's expand and see this. This is what? This is a1 plus a2x plus a3x square and so on, which is equal to 2ax. Okay, let me just switch the order so that. Now, if I multiply this entire equation by x and divide by x, am I okay or not okay? Can I divide this by x equal to 0? Yes, anybody? I am suggesting this. And I will add a term a0 here and subtract a term a0 here. And this entire thing I do by x. Is this allowed for me or not?
Not if x equals 0.
Yeah. So when x is equal to 0 in this entire setup, what really happens? You're looking at a of 0. A of 0 is what? x0. So vanishes. A0, which is given to be 0. So I already have value for A0, right? So I can here assume that x is not 0 and I can do this manipulation. Fine.
Ma'am, so what is this polynomial? Is it just a formal expression or is it having some convergence kind of?
See, as of now, we don't even know what this series is. So forget about its convergence. We are trying to find these values a n. And depending on what these values a n are, it would determine whether this series is convergent or not, right? But that is not the question here. Here, the question is, can this particular expression be divided by x? Or rather, can this be divided by x?
Ma'am, if A0 was 0, then we couldn't have done this, right?
Right. Even if a0 was 0, thing is, for x equal to 0, I already know the answer.
Okay, okay.
X equal to 0 is actually just the a0. So we ignore that part and we come here, and this inside thing now you can see clearly is ax, but I have subtracted one term because I had to add this here, right, to attain ax, and this divided by x. Now this solving is easy. You have 2x ax equal to ax minus a0, which now further tells you that ax is equal to a naught over 1 minus 2x, right?
Yes.
And a0 was, oops, I should not have written 0, this is 1. With a0 equal to 0, this entire thing will be 0 sequence, right?
Yes.
Hello? Did I make a mistake? Oh, no, okay. Here it was fine. So this is nothing but 1 upon 1 minus 2x. And this everybody knows expands as 1 plus 2x plus 2 square x squared plus 2 cube x cube and so on, correct? So this is nothing but, this everyone recognized, right? 1 upon 1 minus t. And then you can write this as 1 minus 2x raised to minus 1 and then use the binomials. So this can be written as 2 raised to n, x raised to n, and be written equal to 0. So now this, which was actually, oops, hello?
Hello.
Yes.
Did this disconnect in between again? Is the screen visible? Hello? 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 मुझे खबर क्या हो रहा है? Hello?
Yes, ma'am.
Is it getting disconnected again and again?
Yes, ma'am.
Yes, ma'am.
So when I was explaining, till what stage could you guys see?
That 1 by 1 minus 2x thing till that. And right now we can't see your screen. Okay, yeah, we can see it now.
Okay. Okay, so 1 upon 1 minus is still here, right?
Yes, yes.
Okay. So 1 upon 1 minus 2x is what we see this as. And then if you recall, 1 upon 1 minus t is nothing but 1 plus t plus t square plus t cube and so on, correct? Using the simple
Yes, ma'am.
binomial expansion. So this is how we get that 1 upon 1 minus 2x is 1 plus 2x square, which I have written as 2 square x square, 2x cube and so on. And then this I write as summation 2 raised to n xn, n starting from 0. But then this is nothing but the, because what we have evaluated is the ax, correct? And ax was an x raised to n, n starting from 0. So comparing these two, what I get is that an is 2 raised to n for n greater than or equal to 0. Correct? So this is the
Yes, ma'am.
final answer. Oops. Does this match with what we had guessed earlier? Yes, it does. Okay, so far so good. Now, if instead of a baby example, we take something little less intuitive, let's take an plus 1 to be 2 raised to an plus n. I just add this term n here. Okay, and similarly n greater than or equal to 0 and take a0 to be 1, just as before, and see how it is. So given that a0 is 1, a1 is 1 into 2 plus 0, so this is 2. a2 is 2 into 2, 4 plus 1, 5, and few more times, so 12, and so on. Is it easy to see what this is? Can you tell me what it is? Any guesses? Anyone? If you don't have a guess, you have to say, no, ma'am, we can't guess, so that then I can proceed further. Okay. So anyone has any guess for this term an here? No? Then let's come to the thing which we just learned. We try to find it using the generating function. So we want to express this as an xn summation running from n equal to 0 to infinity. Okay, so we want to see what this turns out to be, whose coefficient for the nth power of xn, x is going to be the nth term of this sequence, right? So as before, what we're going to do, we're going to multiply each term of this particular sequence by x raised to n, and then sum them over from 0 to infinity. Okay, so I have to make this. So we are going to get an plus 1 . Hello?
Yes, hello.
I think it got disconnected again, right? Is the screen visible? So this is 2 times summation an xn n greater than or equal to 0 plus summation n xn n greater than or equal to 0. Okay. God, कितनी बार disconnect हो रहा है? Hello.
Yes, hello.
Yes, ma'am.
Hi, I don't know how many times it has got disconnected so far. So we were here. We started with this sequence an plus 1 equal to 2 times an plus n. And then since we could not guess from the terms which we tried evaluating, we came down to the generating functions. So ax equal to summation an xn summing from 0 to infinity. And as before, we multiply each term of this particular formula by xn and sum from 0 onwards. So I get this particular equation here, right? And this, as before, we'll manipulate and get that ax minus a naught over x. And this thing is same as ax, so 2 times ax, and this is here. So far, so good?
Yes, ma'am.
Yeah.
Now, so rest of the things are fine. This looks what is not so familiar to us, right? So let's see a small trick. If I rewrite this particular term, or forget about this part, just see nxn. So tell me if I'm right. So can this be written as, or rather, I write this as x.
Ma'am, is it x by 1 minus x whole square?
Yes. So seems like you have already done this sort of thing. Okay. So this thing, can I write as this? When I do d dx of x raised to n, I'm going to get n x raised to n minus 1, right?
Yeah.
So this will become n x n minus 1. So then this, when you expand, you're going to get n x raised to n minus 1 plus 1. So this is nothing but n x raised to n, which is what I started with. Correct? So this is the trick we are going to use here to evaluate this particular summation. So we write this summation n xn, n greater than or equal to 0 as summation x d dx of x raised to n, n greater than or equal to 0. Okay, but this x is independent of n now, so this can be taken out of the summation, right? So, and so is this. So let me just take all of it out at once. So d dx of whatever stays inside, which is x raised to n. Now this everyone knows is, yeah, quickly please. What is this?
1 by 1 minus x equal inverse.
1 minus x inverse. And then when you differentiate it, we are going to get one minus x inverse square, correct? Which is actually this, correct? Everybody is with me so far?
Yeah.
Now we go back and plug it in this expression. What was a0 again? 1. So here we'll put 1 and here we'll put what we have just achieved and see what it becomes. So you have ax minus 1 upon x is equal to 2 times ax plus x upon 1 minus x whole square. Fine. So let's just remove this, put an x here, put an x square here, and then I know that 1 minus 2x ax is equal to x square upon 1 minus x whole square. This particular one I'll bring here. So ax is nothing but 1 plus x square upon 1 minus. See, I'm very bad with this sort of manipulation math. So you should check along with me if I'm doing it right or not. Correct? This is what I get ultimately. Is this what everyone has got, or I've made a mistake somewhere? Is this correct?
Yes.
Yes.
Now from here, everyone knows what to do. You expand this, you bring it down in some px over, sorry, qx form, and then use partial fractions. Right? And arrive at the answer. So this was all when you had only two terms of the recurrence, an plus 1 and an. What happens if you have actually three terms? Maybe you guys have any lecture after this also?
Actually, we have an orientation from 6:30.
Oh, okay. Then I'll not keep you people here. But is there any other slot which is available? Time slot? So I see so far I have only MSc Computer Science first year, second year, and MSc Maths second year, right?
BSc second year.
BSc second year also. Okay. So do we have a slot which is earlier than 5 p.m. which is available to all of us? And instead of a 1 hour 15 minutes, I would hold probably 1 hour 30 minutes lectures. Is that fine with people?
Yeah.
Or otherwise we'll hold 1 hour lectures, but then we'll meet thrice a week. So how about 3:30 to 5?
From 3:30, we have a class on every day. I'm speaking on behalf of the MSc first year students, computer science.
Okay. And mornings 11 to 12:30?
On Monday and Wednesdays, we have classes.
Other days it's available?
Yes, it's available for me at least.
Okay, 11
I
to
think-
12:30 others?
I think maybe we can,
Sorry?
maybe we can discuss it and then let you know. Or some, I mean, is there some preferred time for you? So maybe we can discuss it among ourselves.
I mean,
because
these are the two slots which I would have preferred over other slots, 11 to 12:30 or 3:30 to 5.
Okay, maybe. Okay, fine.
And
5 to 6:30 will be fine if you can take it. 5 p.m. to 6:30 on other days. Today we have an orientation, but that's not.
5 to 6:30 is not so comfortable for me. That's why
Okay.
I am not restricted to days. I am restricted to times. But it's okay. If nothing works out, we'll meet 5 to 6:30. Okay. If we are not able to meet every lecture, we'll try to meet at least once every week, and the other lectures will come as video recordings. Okay.
Okay.
And yeah, I forgot to mention, so about the office hours, they're always by appointment. So my email address is shuchitag@cmi.ac.in. Let me just mention it somewhere so that you can take a note of it. Or wait, I could have written it on the whiteboard. No? Okay. So where is my pen? So office hours by email appointments. Okay. And please email at least a day or two prior. Don't expect me like you'll email me by 1 a.m. of, let's say, nth day of the month and ask if we can meet at 10 a.m. on nth day. Won't work. Okay. You can give what is your query, and then I mean, we can pick up a day when both of us are available. If not in the office hours, like the usual 9 to 5 office hours, we can have even like a 8 p.m. or something. Whatever suits the both the parties. Fine? Hello?
Okay, ma'am.
Yes.
Yes.
Yeah, so it's always by email. I repeat, always by email. If like after this is scheduled, like we know who all are the students, then we'll form a WhatsApp group, and rest of the like mini discussions will happen on the group there. Okay. But that we'll do once the final list of students is prepared. Fine. So, okay, so next class is day after tomorrow on Friday. Hopefully it will not disconnect this much as it did today. And we'll see what happens when the sequence, like more than 2 terms of the sequence are available, or if the sequence comes with some boundary problems, how we tackle them. Okay. If you have any doubts
Okay,
from today's class, you email me. My email address, did I give my email address? I don't. This is what I do. Okay. So email, preferred email is this. Like I'm more likely to check this one. And this also you can write to. Okay. Fine.
Okay.
Yeah. So with this, let's send today's lecture. We'll meet day after tomorrow. As I said, if you have any questions, any doubts, anything, write back to me, preferably on my Gmail ID. Just for the reason that I check that more often. So it's a quicker way for me to get back to you. Okay? Sure.
Okay.
Bye.
Thank you.